All right. Hi, everyone. Thanks for coming. Were you about to say something? Oh, okay.
From Department of Statistics, the postdoc here, and he's going to be telling us about optimal transport.
Great, thanks. Yeah, as I was saying, thanks for coming. As Daniel mentioned, I'm a postdoc in the statistics department, so I'm not too far from where some of you guys probably hang out. So please come and say hi if you have any questions or are interested in doing research in optimal transport. Always happy to chat. All right, so the plan for the 2 hours that I'll cover of this session on optimal transport is to kind of give you some introduction to the concepts that I've found useful reading papers in optimal transport and doing research in optimal transport from the perspective of a statistician. So we'll go through some of the basics, the foundations. In the first part, in particular, we'll phrase what are called the Monge and Kantorovich problems, discuss the nature of these problems and their solutions and stuff like that. In particular, we'll look at what's called the primal and dual formulations of these problems. They both shed light on the solution to these Monge and Kantorovich problems. And then we'll cover a special case that's quite important in practice. It's perhaps the most famous special case of an optimal transport problem. It's the Wasserstein Distance, which I'm guessing some of you have heard about by now, and discuss some of its important properties. The second part, after the break, will be more focused on computation and to a lesser extent applications, but focused on computation. We'll talk a little bit about how to compute optimal transport costs exactly, and then look at mainly one approximate scheme for calculating optimal transport costs. And the advent of fast approximate solvers is really what has led to optimal transport seeing a bit of a resurgence, especially in the statistics and machine learning communities. And this will segue into some of the statistical properties that we might be interested in as people who are learning from data, which we will also discuss when we talk about the optimal transport as a loss function. And then we'll look at an application from generative models. Does that sound good? Good. So if you have any questions, please shout out whenever. All right, so let's look at some of the theoretical foundations first. So arguably the first optimal transport problem was phrased by Monge back in 1781 in his theory of what he called Deblay and Ramblay. And so Monge was interested in mining applications. And so the kind of problems that he was interested in was, well, suppose you have Deblay, think about it just as dirt or a raw material of some kind that you want to excavate and transport some distance to a particular location where it's going to be used to build, for example, an embankment or some structure, which he called Ramblay. And there's naturally a cost associated with transporting mass from one location to another. You know, you have to pay someone to do it, or you have to do it yourself. It costs you energy and time. And so over all possible ways of achieving this transportation, that is, take the mass located at a point X and map it to a location Y, so that you transport it from the mine to exactly the structure that you want to build. You want to minimize the overall cost of doing this transportation. And there are many possible ways you could do this transportation, potentially, right? So Monge made a lot of progress on this problem, despite not having access to the modern mathematical tools that we have today, guided by a very keen sense of geometry. And geometry is really at the heart of this problem, and we'll talk more about that later. So this is actually a figure from his 1781 publication. Just pretty neat, I think. So let's put this problem that Monge was interested in into modern language. Excuse me. And so the mass that you want to excavate, we can think about it as a distribution, right? There's a total mass that you want to excavate. You can normalize that to, say, be equal to 1, and discuss transportation as transporting fractions of the total mass, right? So we can think about the mass as a probability distribution mu here in blue, which we want to transport to distribution nu here in red. As we discussed, there's a cost associated with transporting stuff in the real world, and so there's a cost function that defines the cost of transporting a unit of mass from a point x to a point y, right? And with these two constraints, that this is our origin, this is our destination, and we have this cost function that describes moving a unit of mass from one point to another, Monge wants to find a map, T, so that the blue distribution gets mapped into the red distribution. That's what this constraint here says. This denotes the push-forward measure of mu via T. I'll talk a little bit more about that in a second. And given that, over all possible such maps, we want to minimize the total cost, right? That's what this problem here says. And we're also interested in finding minimizers, right? By the way, to say more about this notation, the push-forward map of mu via t, you can also think about this way. So suppose x is a random variable distributed as mu, and you apply t of x to that random variable. This is distributed as the push-forward of mu by t. Oh. Is this... No problem. Okay. So this is the kind of problem that Monge was interested in. But we can already see that there is kind of a lack of flexibility in this problem, right? Suppose that we flip the roles of mu and nu. Suppose we wanted to transport the red distribution to the blue distribution. We cannot really achieve that with a map in the standard sense, because you cannot say that all the mass at location y should be transported to two different locations with a map, a traditional notion of a map, right? A function. And so there is kind of, this problem makes sense, but only sometimes, right? There are some conditions necessary to make this problem well-defined. By the way, you can think about these blue arrows here as representing this map. And so this map might well be optimal, because it makes more sense to transport these four guys to the closest destination y than it does to send them all the way up to this big guy over here, right? Do you agree with that? That is intuitive in this sense, if you think about the cost as being the distance on the page here. Good. Right, so this kind of lack of flexibility is what Kantorovich was faced with in the 1940s, so some 150 years later. So Kantorovich was a Soviet mathematician and was particularly interested in the optimal allocation of economic resources, right? That's important. It was important for the Soviet Union with their planned economy. And he developed the theory of linear programming to tackle problems of this kind, for which he won the Nobel Prize in economics in the 70s, I think. Another problem that was facing the Soviet Union at the time, which consumed a ton of economic resources, was the war. And so one kind of question that Kantorovich was interested in was, suppose that you have soldiers distributed in Russia in some location, some barracks, say. You have 150 of them here, or 150,000. 90 of them here, 60 of them here. And it's been determined that 120 of them need to go to this battlefield, or else they're going to lose this battle, right? 90 of them need to go here, and another 90 need to go here. And so with Monge's way of tackling this problem, we wouldn't be able to really satisfy these constraints, right? Because we couldn't send 150 soldiers to, say, this place where we need 120 with a map without also, not being able to supply as many soldiers necessary for one of the other battlefields. Do you agree? So we need some notion of splitting, right? We need to split up the mass, if you will, located at these 3 barracks, right? We need to be able to say that, okay, 60 of these soldiers go here and another, amount go to the other destinations. Does that make sense? Do you see how these 2 problems relate, but they are slightly different? Okay. And so it makes sense to think about sending fractions of the mass located at each of these points. And that can also be naturally represented with a probability distribution, and in this case, a joint distribution. So Kantorovich formulated this problem like this. Again, we have 2 distributions, mu and nu. We want to transport mu to nu, or the other way around. And there's a cost function in the same way that Monge was thinking about a cost function. But now we are allowing mass at one location to be sent to several destinations. For example, here, this joint distribution pi here says that some of this mass at the point y gets sent, or say 50% of it gets sent to this location, another 50% gets sent to this location, right? And we can represent this by probability distribution, where probabilities describe the fractions of mass at one location getting sent to another. Yeah? And so we can minimize a very similar objective function here. We're still interested in minimizing the total cost, but now we minimize over joint distributions, or what we call transport plans, that have mu as one of its marginals and nu as one of its other marginals. We call this a set of couplings. And again, we're interested in a minimizer, potentially. All right, does that make sense? Good. So these problems come from kind of thinking about the optimal allocation of economic resources in some way. But that is, I guess, somewhat far removed from the papers that you might have read recently about, I don't know, generating images and stuff like that using the Wasserstein Distance as a loss function. So where does the power of optimal transport come from in those domains? Well, we'll say more about it later, but I think to summarize it in one sentence, optimal transport provides use or a natural vehicle to lift the geometric structure captured on the base space up to the space of probability distributions over that base space. So you can now compare probability distributions in a way that incorporates the notion of geometry captured by the cost function that you have on the base space, right? And this is important, or it could be important, in any application where the geometric domain is important. For example, here in computer graphics, where you want to interpolate between different shapes, or it's been argued that if you want to take or calculate the notion of averages between different brain scans, you're better off doing that in a way that incorporates some notion of geometry of the brain. Or in modeling the evolution of ocean temperatures, where there's a geometric effect determined by the shape of the coastline. Right? So optimal transport has been used to model all of these 3 pictures come from papers that use optimal transport for these purposes. So that's kind of an abstract view of why perhaps optimal transport has become useful, or is useful, I should say. All right, so let's go back to these 2 problems. I defined 2 optimal transport problems for you. So the Monge problem, we'll call it MP, and the Kantorovich problem, we'll call it KP. By the way, do you all understand the notation I'm using and stuff like that? Any questions about these problems? No, good. Oh yeah? Yes, so they both describe transport plans. The difference between them is that in this problem, we're looking for a map which says that all the mass at a point x will be mapped to a point y. That's kind of our notion of transport plan in the Monge problem, right? And so we're constrained to look for plans that say, take all the mass at a point x, map it to a point y. On the other hand, in the Kantorovich problem, we have some more flexibility. So when you're at a point x, you can decide to map a fraction of the mass at a point x to a destination y, and another fraction of the mass at a point x to a destination y primed. And this we can describe with a probability distribution that describes kind of the fractions of mass going to each destination. So that's the difference between these two constraints here. It's deterministic operator, yeah. So it's a function in the normal sense, right? It can only map to one point. And so the push forward is defined in this way. Push forward measure is defined in that way. All right, so we've already said a little bit about how these two problems relate. One thing to note that if you find a feasible map for the Monge problem, that induces a feasible solution to the Kantorovich problem. You can take pi to be the push forward of the identity map and t of mu. Well, I'll show you a picture of what this might look like in a second, just if it's hard to see. And we also said that the set of maps that achieve the transport between mu and nu might be empty. Remember, that's what we discussed on the second slide when we discussed the Monge problem. There might be no map that achieves the transportation between two distributions. On the other hand, the set of couplings is always non-empty. For example, the product coupling, the product measure lies in the set of couplings. And so there's kind of more flexibility in this problem than in the Monge problem. So this is what it might look like. So in the Kantorovich problem, we're looking for any joint distributions between these two marginal distributions that respect the two marginals. Sorry, that's the feasible set. Any distribution that respects the two marginals is the feasible set. And then we're looking for the one that minimizes that cost function. On the other hand, in the Monge problem, we're looking for something much more degenerate in some sense. The joint distributions that we're allowed to look for in the Monge problem have to be supported on a map, right? So they'll look kind of odd like this. They have to be supported on the graph of a map, right? And this is obviously a special case of a coupling, right? And so solutions to the Monge problem induce solutions to the Kantorovich problem, or feasible solutions to the Monge problem, Kantorovich problem. So this is the one we'll focus on mainly, and we'll discuss connections to the Monge problem later. And so this is what we'll call the primal problem. But we haven't really, I've written this down for you, but we haven't really discussed some of its important properties yet. For example, does a minimizer exist, or is this just kind of a vacant statement, right? If it does exist, does only one exist, or could there be many? And what do they look like? What can be said about the structure of the minimizers to this problem? Which are important questions to tackle. And we'll tackle the first one first, directly from the Monge problem, from the primal problem, the Kantorovich problem. And if this doesn't make sense to you, don't read it. We'll talk about kind of the intuition here in a second. So if X is a Polish space is a complete and separable metric space. If that doesn't make sense to you, just think about X as being some Euclidean space, That's the easiest thing to think about under its canonical norm. And suppose that C is lower semi-continuous. If that doesn't make sense to you, just think about it being continuous. Then the Kantorovich problem does have a minimizer. And what's the idea behind the proof? Well, define this functional, right? It takes a pi, a coupling pi, and evaluates the cost associated to it. We can, under the lower semi-continuity assumption on C, we can show that this functional is lower semi-continuous. And we're minimizing over a compact set. The set of couplings turns out to be compact. So these are functionals and subspaces of the space of probability distribution. So we need a notion of topology for that space. And the notion of topology that's appropriate in this case is the topology of weak convergence. How many people know about what weak convergence is? Okay, so I'll define it real quick then. Not that it matters too much, but just so that I don't throw out too many terms that people aren't familiar with. So we say that the sequence of distributions, mu n, converge weakly to distribution mu if for all functions that are continuous and bounded, that's what this notation means, we have that the integral of f against mu n converges to the integral of f against mu as n goes to infinity. Okay. So this gives us the required topology. Compactness of the set of couplings you can show with Prokhorov's theorem, and you can show lower semi-continuity of this functional by approximating C from below with continuous and bounded functions. Show that K is equal to the supremum over the corresponding integrals, and by monotone convergence, and that gives you lower semi-continuity of this functional. All right, so at least we know that the problem isn't completely kind of empty, void. We know that there exist minimizers. But to discuss the nature of the solution more carefully, we need to, or it can be useful to derive what's called a dual problem to this. If you've done any linear programming or something like that, you know that there's, for minimization problems of this kind, like we're minimizing something that, in this case, happens to be linear in pi over what happens to be a convex set. There's kind of a, it's often helpful to think of I guess an analogous maximization problem that can shed more light on this solution. And that's what we'll do next. So to derive the dual problem, first note that this constraint here, that pi is in the set of couplings between mu and nu. That is, it's a joint distribution that has mu as one of its marginals and nu as the other marginal. This constraint can be encoded as follows. Take the supremum over the integral of phi against mu and the integral of psi against nu, and subtract the integral of phi plus psi against pi. Then if pi is a coupling, then this happens to be 0. If it's not a coupling, it happens to be infinite. Let's think about that for a second. So what happens if pi is a coupling? Well, this becomes the integral with respect to the first marginal mu, which happens to be nu, and so this guy and this guy cancel, right? And then the same thing happens with this guy. And so for any psi and phi and psi, this thing is 0. And so maximizing over it will also be 0. On the other hand, if it's not, if there is some discrepancy between a marginal of pi and, say, nu, then where they are different, we could choose phi to blow up, right? And so we could make phi as big as we possibly wanted or as small as we possibly wanted at a set where the marginal of where mu and the marginal of pi disagree, right? And so if it's not inside the set, we can send this supremum to infinity. By the way, don't worry too much about these constraints. This is just to make sure that these integrals make sense. For our purposes, is to make sure that these integrals make sense. Does this make sense to you? Are you all following? If I'm going too fast or going too slow or boring you, please let me know. All right, so with this formulation of the constraint, we can replace the set that we're minimizing over by instead incorporating this essentially as a penalty. And it's a penalty that's 0 if the constraint is satisfied, the earlier constraint is satisfied, and it's infinite if it's not satisfied. So this is the same maximization problem as the one, minimization problem as the one we considered earlier, right? Now, what we're minimizing over are positive measures. But if we interchange the order of the minimum and the maximum here, by the way, this needs formal justification, and we'll mention a result later that provides the necessary formal justification, but this you can't do willy-nilly, right? You have to check that this makes sense. But if we do this, we get a different optimization problem, which is now maximizing over the functions phi and psi of these two integrals. But the penalty now is in the form of this minimization problem over pi, right? This is just rearranging from here to here if we're allowed to interchange the operations. And so let's think about what this penalty might mean. Perhaps it has an interpretation similar to the one to the one we discussed earlier. Turns out it does, right? So the minimum over positive measures pi of this integrand is equal to 0 if the sum of phi plus psi, the direct sum, is less or equal to c, right? Why is that? Well, imagine that this constraint is satisfied. That means this integrand is always positive, right? And so what's the smallest we can make the integral over positive functions when we're allowed to minimize over positive measures? It's 0. We send the mass of pi to 0. Pi is no longer a probability measure in this case. What about if this constraint is broken, right? Well, then there exists a point where this integrand is positive. And so we could choose pi to put all its mass at that point where the integrand is positive, right? Negative, negative, negative. Thank you, Daniel. Where this integrand is negative, right? And so it would be negative infinity if this constraint is not satisfied. Yeah? And expressing this in the form of a constraint, we get the following problem. We maximize the integral of phi against mu, the integral of psi against nu, such that the sum of phi plus psi is less or equal to c. This is what's called the dual problem to the Kantorovich problem.
In the previous infinite, require pi to be a measure, or?
It's sufficient for our purposes to restrict pi to be a measure, yeah. But that's kind of the natural relaxation of the constraint as well.
If pi is a measure, how to make it to be 0?
A measure doesn't need to integrate to 1. A probability measure has to integrate to 1, but this is only restricted to be a measure that is positive, meaning it's not a side measure. You can't put negative mass anywhere. All right, so we got to this place by just manipulating formulas, right? And it's not necessarily the most illuminating. So let's think about an intuition for this problem that might help us relate it to the minimization problem we started with. And so let's return to the problem that Monge was interested in, the problem of Debré and Ramblay, or the earth movers problem, it's often called as well. But now let's solve it with Kantorovich's perspective. So we're allowed to look for joint distributions rather than just transport maps. And we know what the cost is of transporting the mass, a unit mass at location X to location Y. Right? That's what we know, and we also know what the marginal distributions are, but perhaps we don't have the resources or are too lazy to compute what the optimal transport coupling looks like. And so we look to hire a company to do that for us. So say we hire a logistics company, and their pricing structure is as follows. They charge us phi of x to pick up a unit of mass at the point x, regardless of where it ends up, right? This is not too different from when you send a letter, for example, right? In the mail, if you've ever done that. Psi of y, they charge psi of y to drop off a unit of mass at y, regardless of where it came from, right? So this is their pricing structure. And so this is they come to us, they offer us a function phi and a function psi, and we decide whether we'll take the contract or not. But we know that the fair price from x to y is given by this cost function that we've decided on ourselves. And so we're not going to accept any offers that charge us more than what we know is the fair price, right? And so this is where that constraint comes from. And the company, under this constraint that they know will reject the contract if they charge an unfair price, the company wants to maximize what they can charge us. And that corresponds to this function here. Right? Does this intuition make sense to you? This is the total charge for the pickup. This is the total charge for delivery. They want to maximize that total charge, but they know that we'll reject it whenever they charge us an unfair price at any location. And so what they're minimizing, or what they're maximizing, is this problem here. Right? So you can see that these two problems are related, but come from two slightly different perspectives, right? And the hope is that by also solving these problems, that will shed more light on the solution of the original problem, the Kantorovich problem. That's the direction we're going. Excuse me. And so here's the theorem again. This is to establish that looking at this dual problem makes sense. If we instead focus on maximizing the dual, we actually achieve the same value as the minimum in the primal problem. There's no gap between them. And so under the same conditions as before that allowed us to establish the existence of a minimizer, we can also say that the minimum of the Kantorovich problem is equal to the maximum of the dual problem, right? This gives us some comfort that looking at the dual problem is important because it allows us to achieve the same value as we did in the primal problem. You agree? And the proof here is very interesting, but a little involved, so we don't have time doing it. Here's a reference. St. Ambrosius' textbook is very good. We can say more, though, at optimality. And this, you really need to look at St. Ambrosius' textbook to be able to deduce. But at optimality, right, so where this Kantorovich problem attains its minimum and where this dual problem attains its maximum, we can relate the solutions in a way. And so the function solving the dual problem or minimizing the dual problem, the sum is equal to the cost function, meaning that the company does indeed charge us a fair price, pi star almost everywhere, meaning that wherever the optimal transport plan puts mass, they will charge us a fair price. This is not something we'll dwell on, but to connect it, if any of you are familiar with convex analysis, which is very much at the heart of this problem, and I encourage you to look into, phi star and psi star, the optimizers, are conjugate with respect to C. This is kind of a generalization of convex conjugates, if you will. And this pi star, the optimizer, the optimal transport plan, is supported on what's called a C cyclically monotone set, which is a bit of a mouthful. And this concept was very confusing to me for a long time. Turns out that it's kind of one of the most important definitions that underlie the study of optimal transport, so it's worthwhile dwelling on it for one slide. So the definition of a C-cyclically monotone set is that for any finite set S, for any finite subset of that set S, you cannot improve the cost by changing the pairing of the x's and the y's. That's what this is. You cannot permute the order of the y's in such a way that you reduce the cost. And this is over all permutations, sigma. And it's not clear how this connects to optimal transport at all, if you ask me, at least not from the surface. But it turns out that very many important properties follow from this property. For example, if you take this important special case where X is a Euclidean space, and we're working with the canonical distance squared, so the Euclidean distance squared, and you assume that the measure mu has a density with respect to the Lebesgue measure, then from cyclical monotonicity alone, more or less, you can derive the following. In this setting, pi star is unique, right? That's saying a lot more about the solution than we were able to say so far, right? What's more is that it's actually attained at a transport map. And so the solutions to, or rather the Monge problem, which we thought was much more restrictive than the Kantorovich problem, they happen to coincide in this case. The minimizer of the Kantorovich problem is also a minimizer for the Monge problem in this specific setting. That's quite impressive. We can say even more about this optimal map. In fact, it's the gradient, it arises as the gradient of a convex function. All these things you can derive from cyclical monotonicity. And this paper here is very good. It's pretty easy to read. You might just have to deal with some mathematical jargon, but I think everyone here can probably understand it if they take the time, and I encourage you to do so. Yes?
The last statement, is it a little bit unsymmetrical? T of x is gradient of phi, not relating to psi?
It's a good point. It turns out from the previous page, it turns out that psi and phi are very strongly related in a way. So if you know phi, you basically know psi. So you could express it in terms of psi as well. But it's a very good question. It does look asymmetric. Any other questions? Okay. So now we've gotten quite far from where we started, right? We defined the Monge and Kantorovich problems, motivating them from the respective problems that Monge and Kantorovich were faced with in their time periods. We show the existence of minimizers. We derive the dual problem and show that this dual problem, combined with some other properties, can be used to derive important features. Kind of gives a quite thorough characterization of the solution to the Monge problem. So let's talk about the Wasserstein distance, which arises as perhaps the most important special case as the kind of optimal transport problem that we've discussed so far. So again, let X be a Polish space now with a metric D. Again, if you don't know what this means, just think about R and the Euclidean distance. That kind of gives you everything you need to know. The Wasserstein distance for some power p bigger or equal to 1, between mu and nu that have finite pth moments, that's what this notation here means. Mu and nu are probability distributions with finite pth moments. Then the Wasserstein distance between mu and nu is given by the optimal transport problem, where the cost is equal to the metric to the power d. And then you take this power in kind of a very reminiscent of LP norm sense, right? This defines the p Wasserstein distance between mu and nu. And so you can ask, well, what's important about this? It just looks like another optimal transport problem. Well, what's quite significant about the Wasserstein distance is that it defines a proper distance on this space. Other discrepancies that you know between distributions, perhaps with the exception of total variation, might not be proper distances on that space, like the KL divergence isn't, and most other information-based distances you can think of, chi-squared, all of those kind of things, don't satisfy these properties. So what does it mean to be a proper distance? Well, it's bigger or equal to 0 with equality if and only if mu and nu are equal. It's the first one. It's symmetric. Both of these you can probably see pretty much directly from looking at this or staring long enough at this optimal transport problem that defines the excuse me, that defines the excuse me, defines the Wasserstein distance. But the non-trivial one here is to establish that the triangle inequality holds for the Wasserstein distance. This will skip, but you can see Villani's textbook, which is also very good, but it's about 900 pages long. So good luck. This relies on something called the gluing lemma, which allows you to establish that there exists a coupling between mu, rho, and nu that has the optimal transport coupling between mu and rho as the marginal of the first two coordinates, and the optimal transport coupling between rho and nu as the two last coordinates, which is non-trivial. But from that, together with Minkowski's inequality, you can establish quite easily that the triangle inequality is satisfied. It's a good exercise if you're interested to kind of get your hands dirty and learn to appreciate these kind of techniques more. And so this kind of illustrates that what I said kind of a little abstractly in the beginning rings at least a little bit true. The optimal transport problem inherits a lot of the geometric information captured by the cost on the base space, in particular, it's also a distance, right? That's pretty important. And so here are some theoretical properties of this space. Sorry, not theoretical, topological properties. If the base space is Polish, then this space of probability distributions with finite pth moments matriced by the Wasserstein distance is also Polish, right? So again, this emphasizes that a lot of the geometric information about the base space is inherited by the Wasserstein distance. That's important, at least in a lot of application or a lot of kind of theoretical study of these kind of distances. This gives rise to things like geodesics on the space of distributions. In turn, that allows us to formalize concepts of Barry centers, or kind of a geometric center of distributions. So you can think about computing averages of distributions in a way that leverages the information known about the geometry of the base space. And this space has a Riemannian-like structure, which was utilized by Otto and other guys to develop what's called the Otto calculus, which allows you to define things like gradients of functionals on the space of probability distributions, like entropy or KL divergence, gradients of those kind of functionals with respect to the Wasserstein distance. And that's very important in applied math. It allows you to say that, for example, the heat equation is the gradient flow of entropy when you define gradients in a formal sense with respect to the Wasserstein distance. So here's a picture to kind of emphasize the difference, or rather how optimal transport is able to incorporate information about the domain, about the geometry here. So these are interpolations or geodesics between two different geodesics between mu and nu. So nu here is in red, the most red curve. Mu is the most blue curve here. And if we take the linear interpolation, which is just a convex combination of these two guys, so say lambda of mu plus 1 minus, sorry, I should do it this way, 1 minus lambda of mu. Lambda of nu. That's this guy. What happens here is basically that as lambda goes to 1, you're just squishing down mu, and out of nothing, basically, comes nu, right? So that's what's happening as lambda goes to 1. You just squish it down, and up from this part of the space, nu arises. The optimal transport coupling, on the other hand, kind of leverages what we know about the geometry, what we know about the location of these two distributions, to define the corresponding interpolation. Here we can see that there's kind of the distributions kind of slide in the space, right? For which you would need to know something about the geometry of the space. They kind of slide into its final configuration, which is nu. And for some applications, this might be more attractive. You could argue that if you show this to someone, they might say that, yeah, this is a more sensible way of going from mu to nu than this way is, right? They are, so in this case, well, they're densities here. So think about mu and nu as densities. In this case, it's just, so this is this density for a small value of lambda. And then as lambda increases and goes to 1, you kind of get this function here. So these are mixtures of mu and nu for different mixture components. I haven't defined to you exactly what the interpolation between the optimal transport interpolation between mu and nu is, but I can, in this case, it happens to be 1 minus lambda of t plus lambda of, of the identity map and lambda times t, and push mu forward using this map, right? So this kind of says that we're starting with mu, and then we're mixing in more and more of the transport map that takes mu to nu. That happens to be what this interpolation is. All right. Another important property, at least for statisticians, is that the Wasserstein distance metrises weak convergence. Remember we defined weak convergence earlier? The Wasserstein distance kind of gives you a metric to capture this notion of convergence with an additional constraint. So to say, here's the definition, if rho k is a sequence of measures that converges weakly in the space p sub p of x to rho, that's to say that it converges weakly in the usual sense, which we defined earlier, and that its pth moment also converges. So this notion of convergence corresponds exactly to convergence in the Wasserstein distance. And why is this important for statisticians, for example, or people who work with data? Well, it says, we need to formalize this more, but it basically says that suppose you only have access to your measures through samples, and you know that these the empirical distribution of these samples converge to the respective measures, then you also know that the Wasserstein distance converges. And so you can learn the Wasserstein distance between two measures by calculating the Wasserstein distance between empirical distributions of samples that you have access to from those measures. Right? This starts to get towards statistical perspectives on these kind of concepts. All right, so here's a special case, which is important, which is when x is equal to r, and we have the Euclidean distance on r. And you probably know what a CDF is, and if you take its pseudo-inverse, you get what's called the quantile function. And these two are not inverses in necessarily the traditional sense, but pretty close to it. And this is another exercise that you can do, but I'm sure many of you have done it already. If you take the quantile function, or rather, if you take a uniform random variable and map it through the quantile function of mu, that random variable is distributed as mu, right? So the push forward of a uniform random, or the uniform measure through the quantile function of mu is equal to mu, right? And if mu is absolutely continuous with respect to the Lebesgue measure on R, so if it has a density, or if it's a continuous distribution, that's another terminology for it, then if you map mu, or if you push mu forward through the CDF, you get a uniform random variable. This is sometimes called the probability integral transform. At least that's the name that I learned it under. And so these two properties together allow us to formulate a transport map between two distributions mu and nu, provided that at least one of them, in this case, let's take mu, to have a density with respect to the Lebesgue measure, right? If we take t to be the quantile function of nu composed with the CDF of mu, then if we take a random variable distributed as mu, then applying this first part to it gives us a random variable distributed uniformly, right? And then we apply the CDF of that uniform random variable, which by this property is then distributed as nu, right? So this gives us a transport map between mu and nu. What's more is that this happens to be monotone, right? The CDF is an increasing function, and the quantile function is an increasing function, so the composition is also an increasing function. At least I hope so, if I remember my math correctly. And it turns out that this monotonicity feature, this monotonicity property on R, right? Monotonicity is an important feature of R that doesn't hold for other Euclidean spaces. This monotonicity property is basically equivalent to C-cyclical monotonicity. And so in this case, we can actually conclude that this is the optimal transport map. So that's the exercise for you. Show that it solves the Monge problem and the Kantorovich problem. And that because of this, you can express the Wasserstein distance essentially as the LP norm between the quantile functions of the two distributions. Right, so this is about as nice as we're gonna be able to represent the Wasserstein distance in any case. And so this means that if you have access to the quantile functions and you can integrate them, you can also compute the Wasserstein distance. It'd be cool if you could find an example. All right, so I'm gonna conclude with that. If you have any questions, please raise your hand. Yeah.
Can you define Wasserstein distance?
Yes. No. So well, I shouldn't say no as conclusively, but the Wasserstein distance defined in this way arises only when you choose a metric here. Yeah. I'm not sure if it's an if and only if thing, that this is only a metric, that this optimal transport problem only gives rise to a metric when the cost function is also a metric. But that's always how the Wasserstein distance is defined, yeah. So it's for a general cost, this does not give you a metric. But it does still provide you a natural notion of discrepancy between two distributions if your cost function is meaningful to your problem in some way. And that's the key here, that if you have a cost function that can be that captures something meaningful about the space that your data lies in, then you can incorporate that into this optimal transport problem to kind of so that your discrepancy kind of inherits that geometric insight that you had about the base space. Any other questions? All right, the next part will be more applied, less dwelling on mathematical formulations. So if that's more your speed, come back in an hour, right? Oh, half an hour? Half an hour. Come back in half an hour.